I'm Sujani, faculty in physics at Institute of Aeronautical Engineering. Today we are going to see the demonstration of Newton's rings experiment. And before we start the experiment, let us see the brief outline of the experiment. First, we need to know the aim of the experiment, then the apparatus required. You need to understand the theory behind the experiment and know the formula, the required circuit diagram or the experimental setup in this case of Newton's rings experiment, the procedure of how to do the experiment, and then a tabular column to tabulate the readings. And we are going to see some sample calculations and also a model graph and how to get the final result. You also need to understand the theory and answer some Viva voice questions at the end of the experiment. Now the aim of the experiment is to determine the radius of curvature of a plano-convex lens using sodium light by forming Newton's rings. You will be given a plano-convex lens which is plane on one side and the convex on the other side. You have to determine the radius of curvature of that plano-convex lens by using sodium light. So why we are using sodium light here is it is a monochromatic source of light. So when light from a monochromatic source falls on an object, how interference happens we are going to study with the help of Newton's rings. Now the apparatus required, traveling microscope. So we have the arrangement for traveling microscope here. A sodium vapor lamp. This is the source of light. From the sodium vapor lamp we get the light. A plano-convex lens. This is the plano-convex lens. You can see here this is the convex surface and this is the plane surface whose radius of curvature we have to find. And a thick glass plate. We are keeping this convex lens on a glass plate. So this is the glass plate on which we are keeping the lens. Then we have a magnifying glass to read the readings in the microscope. So you will use a magnifying glass to read in the microscope. Let us see the description, how we are going to set up the arrangement. A black paper is laid on the base of the traveling microscope. So we imagine this is the base of the microscope. So we lay a black paper over which the thick glass plate is placed. And over the thick glass plate we are placing the lens. Now a parallel beam of light from the source. This is the source. Light coming from the source is made parallel with the help of these condenser lenses. So light that is coming out from the source is made parallel and this is allowed to fall on a glass plate which is inclined at 45 degrees with the horizontal. So this is the glass plate which we are keeping at an angle inclined at 45 degrees to the horizontal. Now the light that is incident on it will get reflected. So the reflected beam is now focused on to this setup where we have put the plano-convex lens. The reflected light is now allowed to fall on the plano-convex lens. Now, as a result of interference between the light reflected from the lower surface of the lens and the top surface of the thick glass plate, you need to observe this very carefully. You have a thick glass plate over which we are placing a plano-convex lens. Now, you have an air gap in between the two. There is a small air gap. If you can see here, this is the air gap in between the glass plate and the plano-convex lens. So the light that is incident on it will be reflected. This BE is the reflected ray from the bottom surface of the plano-convex lens. You see BE. And the ray which is proceeding forward in the air undergoes refraction. Because it is coming from glass to air, it undergoes refraction. And again it gets reflected back from the glass plate. So this ray CD after refraction is going along DF. Now there will be interference between the rays BE and DF. That is, as a result of interference between the light reflected from the lower surface of the lens, that is BE, and the top surface of the thick glass plate, that is DF, there will be interference, and because of the interference we get concentric rings called the Newton's rings. So you can see the rings formed here. You will see this pattern when you view it from the microscope. You will see rings of this type, which we call them as Newton's rings, after the name of the scientist Newton. So it consists of a central dark spot. Why? Because we are seeing these rays in the reflected light. So at the center, what happens? Always they are out of phase and there will be destructive interference. So the central portion is always dark. Now the microscope is focused properly so that the rings are in sharp focus. You can adjust the screws, the rack and pinion screws in the microscope, so that you adjust the distance between the lens, that is the objective, and the eyepiece, so that you will be able to see clear pattern of these rings. They should have a sharp focus, okay, so that you can focus onto each ring. And once you get the focus by adjusting the screws, this position of the rings should not be disturbed throughout the experiment. Now the formula that is required to do the experiment to calculate the radius of curvature is dm square minus dn square upon 4 into m minus n into lambda. So m here denotes the mth ring or the nth ring, or we can also write it as conveniently as d2 square minus d1 square upon 4 into n2 minus n1 into lambda. So what we are talking about here is D1 is the diameter of the first ring, D2 is the diameter of the second ring. Here we are denoting by M and N, mth ring and nth ring. So if M and N, we can number them also as D2 and D1 upon 4 into N2 minus N1. This is the first N1 ring, N2 ring. So the diameter corresponding to the N1 ring or the first ring, D2 is the diameter corresponding to the N2 ring or the second ring, into lambda. Lambda is the wavelength of the sodium light. Let us now see the demo of the experiment. The aim of the experiment is to determine the radius of curvature of a given plano-convex lens using sodium lamp by forming Newton's rings. Apparatus consists of a plain glass plate and a plano-convex lens. We place the plano-convex lens in such a way that the convex surface is touching the plain glass plate. How do we know which is convex surface? After placing the lens, we just rotate it. If it is moving freely, means the convex surface is touching the plain glass plate. If you keep it on the plain side, it will not move freely. So when it is based with the convex surface, it can move very easily. So we are using a plain glass plate on which the plano-convex lens, whose radius of curvature is to be determined, and this is placed on a black base. We are putting on a black base. Now the next one is the sodium vapor lamp. This is the sodium vapor lamp, which gives us monochromatic light of single wavelength, and the wavelength is around 5890 angstrom units. To view the Newton's rings, we use this travelling microscope. So this travelling microscope consists of two scales. One is the main scale and the other is the circular scale. Now let us see the arrangement. So in the arrangement, we have the source of light coming from the sodium vapor lamp is allowed to fall on a lens. The rays that are coming parallel from the lens are allowed to fall on the beam splitter. This is the beam splitter. And the rays reflected from the beam splitter are now allowed to fall on the lens. This is the plano-convex. This is the plane surface and the convex surface touching the thick glass plate. So this is how we are going to see the arrangement. Now let us see. So the light that is coming from the sodium vapor lamp is allowed to fall on this lens. falling on the lens, the rays of light that come out parallel from this lens are allowed to fall on this beam splitter, and we arrange the beam splitter at 45 degrees to the path of the rays, at 45 degrees to the horizontal. So we are placing it at 45. So the rays that come and fall on it after reflection are now incident on the plano-convex lens. So when these rays fall on the plano-convex lens, they get reflected back. The ray that is coming from the bottom surface of the plano-convex lens and the top surface of the plain glass plate will interfere with each other, and we get Newton's rings. And we can see the Newton's rings with the help of this microscope. So you need to see from the eyepiece and adjust the screw. This is called the rack and pinion screw, which is used to adjust the distance between the eyepiece and the objective so that the rings that are formed are well defined. You can move it using this rack and pinion screw, adjust it and see such that the rings are well defined. And you can see two crosswise, one horizontal and one vertical. Now adjust the crosswires such that the center or the point of intersection of the two crosswires exactly coincides with the central dark spot. Here we get a central dark spot because we are viewing it in the reflected light. So once it is focused onto the central spot, we should not disturb the setup. Using this circular scale, by rotating this, you can move the crosswires onto the left, move the crosswires and make the crosswires coincide tangentially with the 15th ring on the left side. By moving this, you can see there is motion. You can move it on either side. So it is moving on to the left. So by moving this, you can move the crosswires and make them coincide with the 15th ring on the left. So this is how it coincides. You can see the coincidence of the crosswires with the 15th ring tangentially. So once the crosswires coincide with the 15th ring tangentially, let us note down the reading. So the readings on the main scale as well as the circular scale are to be noted. So you can see the 0 here. So whatever reading the 0 points, you need to note down. Each division is 1 millimeter here. So you can note down the reading as 46 here. This is in millimeter, and also note down the circular scale. So in some apparatus you may have a vernier, or in some we use the circular. So whatever we use, we need to find the least count of the apparatus first and then multiply the circular scale reading with the least count. So here the reading is say 12 and the least count is 0.01. So we get 0.12. So the reading here is 46 and this is 0.12. The total reading will be 46.12. Now once you finish taking with the 15th ring, again make the crosswise coincide with the 12th ring. Move the crosswires such that they are tangential to the 12th ring, then 9th ring, and so on. Once you finish taking readings on the left, move the crosswires slowly on to the right and make it focus onto the 3rd ring again. Onto the right, 3rd ring. So take the reading for the 3rd ring, again the main scale reading as well as the circular scale reading. Main scale reading plus the circular scale reading gives us the total reading. Note down the reading on the right. So the difference between the two readings gives us the diameter of the ring. Yes, let us quickly understand what we have seen in the demo. The point of intersection of the cross wires in the microscope is brought to the center of the system. When you view it from the microscope, you will see cross wires, two cross wires, vertical and horizontal cross wires like this. Actually at the center, you have it at the center. When you view it from the microscope, you will see two cross wires, one vertical cross wire and the other horizontal cross wire. You will set the cross wires in such a way that is exactly at the center. The dark spot is at the center and then you have rings like this. This is how we adjust the cross wires. Now, slowly what we do is we move the cross wires with the help of the screws we have in the microscope, the horizontal screw for the horizontal motion. We use the screw and arrange it or move it to the left and bring it and make it coincide tangentially to one ring. Okay, so we are moving the cross wires and we are making them adjust, moved on to one side. Say left first we are doing, across the field, counting the number of the rings. We will count. If you see here, this is the first ring, second ring, third ring. Now these cross wires are tangential to the third ring. This is how we move the cross wires. Now the cross wires are set at the 15th ring. First reading we will be taking for the 15th ring and the reading on the microscope scale is noted using a magnifying glass. Similarly, we will move the cross wires to the 12th, the 9th, 6th and 3rd. Means we will be increasing in steps of 3. So from 15th to 12th, 9th, 6th and 3rd. So we are actually coming from the left. If you have it like this, so we are coming from one end. So from 15th to 12th to 9th to 6th to 3rd. Now the microscope is moved in the same direction and the readings corresponding to 3rd, 6th, 9th and 12th and 15th readings on the right side are also noted. Now we will move it on to the right. So we will now start, because we will have to move it only in one direction. You cannot move it back and forth. If you move the cross wires back and forth, there will be backlash error. So make it a point that you will take the readings in one particular order. So from the left you are coming to the center and now we will start with the 3rd ring, 6th ring, 9th, 12th and then 15th. So on the right side also we will be taking the reading for all the 5 rings and the readings are tabulated. So this is how we tabulate the readings. First we note down the number of the ring, 3rd ring. What is the reading on the left side? So for the microscope, we have 2 scales. One is the main scale reading and then the second one is the vernier scale reading. The total reading will always be the sum of the main scale reading plus the vernier scale reading. So the main scale reading you take and the vernier scale reading you get by noting down the division. The vernier scale division multiplied by the least count gives us the vernier scale reading. Least count here means the smallest value that can be measured using that instrument. So once you get the vernier scale reading, you add it to the main scale reading, that gives us the total reading. So now the total reading here is 45.17 on the left for the 3rd ring, on the right it is 43.6. Now we get the diameter of the ring. How do we get the diameter of the ring? If you are talking about the ring like this, this is the 3rd ring on the left and on the right. 3rd ring, this is the 3rd ring. So we have taken the reading for this as A and we have taken the reading for this as B. Now if you want the diameter of the ring, so the diameter will be A minus B. So A minus B will give us the diameter of the ring. And then find D square. All these readings we are noting down in millimeters. That is what we have to note. Once you get the diameter, find the square of it. The square of it is 2.46. So continue for all the readings, for all the different rings we have discussed. 3, 6, 9, 12 and 15. Now let us see one sample calculation. Before the sample calculation, let me tell you about the graph, because the slope from the graph is required for us to do the calculation. Now we are going to plot a graph with the number of ring on the x-axis. So we will take it as 1, 2, 3, 4, 5, 6 and so on, because we need till 15 rings. So we'll be plotting the number along the x-axis and d square along the y-axis, the values of d square on the y-axis. You need to take a suitable scale along the x-axis and the y-axis to accommodate all the values. Now, for each ring, corresponding to each ring, you plot the values of d1 square and d2 square. So that gives us a straight line. So all the points will lie on this line. And we need to calculate the slope of the graph. So how do you calculate the slope of the graph? Slope is always given by dy by dx. Slope is dy by dx. So on the y-axis what we have is d square. So it will be d2 square minus d1 square will give us the dy. And along the x-axis we have the number of the rings. So n2 minus n1 will give us the dx. So the slope of the graph is d2 square minus d1 square upon n2 minus n1. This is the slope. So once you get this value, we are going to substitute it in the formula. Now let us see how to do the sample calculation. We have got the slope using this formula. Now the radius of the curvature r is slope upon 4 lambda. So whatever slope we got here, we are going to substitute it here. The wavelength of the light sodium vapor lamp we are using, it is fixed 5890 angstrom. Now we have d1 square is 2.46, of course millimeter square, d2 square is 9.06 millimeter square, and we have considered the third ring, the diameter between the third ring, and then for n2 we are taking as 6. Now let us how to calculate the slope. I have shown you. d2 square is what? 9.06 for the slope minus 2.46 upon 6 minus 3. This gives the slope. And the slope is 2.2 into 10 power minus 6. Why we are writing minus 6 is because we want to write it in meter square. Everything is in millimeters. So we need to convert it. So we are writing it as 10 power minus 6. Now when we have to calculate the r value, r is equal to slope upon 4 lambda. So what is the slope we got? 2.2 into 10 power minus 6 upon 4 into lambda is 5890 angstrom. So we will also write it in meters because we have written this in meter square. So 4 into 5890 into 10 power minus 10, that gives us around 0.93 meters. So this gives us the radius of curvature of the given plano-convex lens. Now we will project the result. The radius of the curvature of plano-convex lens is 0.95 meter. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.